Now that we've talked about the Milky Way and other galaxies, we're starting to get larger and larger into bigger and bigger scale. So now we're going to head out into cosmology. Cosmology is the study of the universe itself. But before we get there, we're going to take a few other steps to help us understand exactly what's happening in the universe. But first, we're going to begin with a question to see if you remember something from a previous time. How did we determine the mass of our galaxy? So think back to when we were talking about our own Milky Way. How did we actually figure out its mass? A, by comparing it to other galaxies whose mass is known. B, by looking at the motion of stars near the edge of our galaxy. Or C, through gravitational lensing of nearby stars. Go ahead and think about it, see if you can remember. We'll discuss it in a bit. All right, so the correct answer is B, by looking at the motion of stars. Okay, so when dealing with galaxies, because we have the mass all spread out, we can't just look at the motion of a single star to figure out what's going on. Instead, we have to, the motion of that one star tells us about the amount of mass inside of that star's orbit. So to figure out the mass of the entire galaxy, we look at these stars right at the very edge. So to kind of help us understand the amount of mass and the mass distribution within our galaxy, we make what are known as rotation curves. Okay, so on this graph, along the bottom, we have the distance from the center of the galaxy. So right here, this is the central bulge, and then we're working out all the way over to the very edge of the galaxy. Then up and down, we're looking at the speed of the stars. How fast are the stars moving? This really quick ramp up here at the very center of the galaxy, at the left side of this graph, this is the central bulge. As we progress through the central bulge, we're adding lots and lots and lots of mass, so stars get going really, really fast. Out here, we actually enter into the disk. Okay, then, towards the very edge of the galaxy, based off of the amount of mass we see that as we get towards the edge of the galaxy, there's less and less stars and less interstellar medium. So we would expect to see what's known as a Keplerian drop-off, that these stars towards the edge should start slowing down. We're not adding more and more mass anymore, so instead this material should slow down. Okay, that's what we expected. However, what we actually found is this top curve, okay, where it does not actually decrease, and instead it kind of levels off, maybe even increasing a little bit. Well, this leaves us with some problems. Either our physics doesn't work, or there's more matter that we are including, it's just of material that we don't actually see. Well, the leading accepted hypothesis is that there is more matter, it's just of stuff we don't see. We refer to this stuff as dark matter, because we don't see it. We'll discuss the exact name in a little bit more detail in a bit. Based off of observations from globular clusters and so on, it appears that our Milky Way is actually embedded in the center of an overall dark matter halo. Okay, so here we have the Milky Way in the center, and then we have this spherical region of dark matter surrounding everything else. Now, one thing that we can say for certain about dark matter is that it is not luminous. Luminous meaning it's giving off light. If there's this much of it, and it's surrounding us, and it was giving off light, it would be easily noticeable. And yet we don't see it, so we can be certain that it's not giving off light. Here we have rotation curves for 4 other spiral galaxies, and notice in each case, out towards the edge, none of them are showing that drop-off that we would expect. Okay? All of these are flat all the way out to the edge. This, again, suggests that it's not just our Milky Way that contains dark matter, but these spiral galaxies do as well. In fact, we can do similar things. We can't actually make a rotation curve for an elliptical galaxy, but we can do other things to figure out their mass, and they also show that there's dark matter in them. Now, based off of what we can tell off of this observation, there needs to be about 10 times more dark matter than the luminous matter. There's 10 times more dark matter than the stuff we can actually see. Okay, so it appears that all galaxies actually have this. Now there's another way of actually determining the mass of an object. This is through gravitational lensing. We talked a little bit about gravitational lensing back when we discussed black holes. The idea of gravitational lensing, we go back to the idea of the general theory of relativity. This states that an object of mass will curve or bend space-time. So you put in a massive object, space-time curves, and then objects traveling through space-time will also curve because of the curvature of that space-time. We used an analogy of a bowling ball and a trampoline. Well, the exact same thing is going to happen to light. If you've got a massive object, then as light is traveling by it, it will curve because of the curve of space-time near that massive object. Well, if we know the path that the light should take, and we know that the path that it does take, how it has been bent, that can then tell us the amount of mass bending it. So in this case, we have some distant galaxy, and then a massive galaxy, and then us. Well, the distant galaxy's light is actually going to get bent as it travels by this massive in-between galaxy. So from our point of view, because of gravitational lensing, we can actually see duplicate images. Okay, so that's exactly what's going on in this image. These two blue spots on either side, those are actually caused by a galaxy that's even farther away behind this galaxy, and that galaxy's light has been bent, so we get this double image. Okay, so knowing where the galaxy should be and seeing the separation, that will tell us the amount of mass of this yellowish galaxy here in the middle. Okay, if the alignment isn't exactly right, then instead of getting the nice blue spots, we can get these arcs and lines and bends and all of these other sorts of things. But all of those will tell us the amount of mass of the galaxy in between that's actually lensing the light. Okay, well, these observations, these studies, give us the exact same answer for the amount of mass in a galaxy. They agree that there needs to be about 10 times more dark matter in these galaxies than the luminous matter that we actually see. So we now have two different types of observations that are actually giving us the exact same answer. In other words, dark matter has to exist. Well, we can actually do a similar thing to figure out the amount of mass of an entire galaxy cluster. So not just a single galaxy, but a whole bunch of galaxies together. So these bluish streaks that we see throughout this image, these are actually a more distant galaxy whose light has been bent through this galaxy cluster. Well, we can do the same idea. We see how the light has been bent, and that tells us the amount of mass in the galaxy cluster. When we do this, our dark matter problem doesn't go away. Instead, it actually gets worse. In this case, it's up to 100 times more dark matter than luminous matter. So on the scale of a galaxy, it's about 10 times. On the scale of a galaxy cluster, it's about 100 times more dark matter than the luminous matter we actually see.